Welcome all. In last lecture we have seen a asynchronous up counter in which counting starts in increasing order, whereas today we are going to learn a asynchronous down counter in which starting will start in a decreasing order. As counting progresses in down direction, these counters are called as a down counters. As we studied in asynchronous up counter, first flip-flop receives external clock pulse and Q output of previous flip-flop is connected as clock input to the next flip-flop. But in asynchronous counter, instead of connecting Q output as a clock input to the next flip-flop, a complementary Q output is connected as a clock input to the next flip-flop. This is the diagram for 3-bit asynchronous down counter in which 3 flip-flops are involved, 3 JK flip-flops are used, and JK terminals of all the flip-flops are connected to logic 1. First flip-flop receives external clock pulse, whereas the next flip-flops in this counter receives complementary output as a clock input from the previous flip-flop. Each flip-flop is a negative age triggered flip-flop. Initially we consider all the outputs of the flip-flops are in reset condition. Therefore initial values of asynchronous down counter will be 0, 0, 0. We will see the operation. Before the application of clock, we assume the output as 0, 0, 0, that is QC 0, QB 0 and QA is 0. Now, as soon as first negative edge of the clock hits this flip-flop A, it will toggle. Now before that, here we will write down the complementary output of the flip-flop also. As here QA is 0, QA complement will be 1, QB is 0, QB complement will be 1, QC is 0, QC complement will be 1. Now, as the first negative edge of the flip-flop clock hits this flip-flop A, it will get toggled, by which this QA will change to 1. As QA is changing from 0 to 1, this QA complement will also change and it will change to 0. Means here QA complement is changing from 1 to 0. So this flip-flop B receives the negative edge of the clock. As we know, this is the clock 1 0 1 to 0 transition consists of negative edge of the clock pulse. Therefore this flip-flop B also gets negative edge of the clock, by which flip-flop B gets toggled. Therefore this QB changes to 1 and the QB complement changes to 0. Now here QB complement is changing from 1 to 0. Therefore this flip-flop C will also get the negative edge of the clock. Therefore it will also get toggled and the value of QC changes to 1 from 0. So after first negative edge of the clock, we will get the output as 1 1 1 and its state number is 2 and its decimal equivalent is 7. So initial value was 0, and the counting, when counting starts, it will starts from 7, the maximum value of this counter. Now we will see the operation at the second negative edge of the clock pulse. Before the application of clock, I will write all the output of flip-flops 1 1 1. As the normal outputs are 1 1 1, their complement output will be 0 0 0. So as soon as the second negative edge hits this flip-flop A, its output get changed, and this 1 will become now 0. Now as QA change, this QA complement will also changes. This 0 becomes as a 1. Now this QA complement is changing from 0 to 1. Therefore this flip-flop B receives the positive edge of the clock. Therefore it will not get toggled, and this QB becomes QB does not get changed. It will remain as it is. So this 1 will remain as a 1, by which this 0 will remain as a 0, and which is connected as a clock input to this flip-flop C. Therefore flip-flop C receives the 0, which is a negative level. Therefore it will not get toggled, and this 1 will not get changed. It will remain as it is. So after second negative edge, we will get output as a 1 1 0. Its state number is 3 and its decimal equivalent is 6. Now we will see the operation at the third negative edge of the clock. Before the application of the clock, the outputs are 1 1 0 1 1 0. Their complemented output will be 0 0 1. Now as soon as third negative edge hits this flip-flop A, it will get toggled, by which this 0 will become as a 1, and this 1 will become as a 0 QA complement. Therefore the change in QA complement from 1 to 0 will give a negative edge to the flip-flop B. Therefore flip-flop B gets toggled, and its output will change to 0 from 1. So as this QB is changing to 0 from 1, this QB complement will change to 1. This 0 to 1 transition will give positive edge to this flip-flop C, by which it will not get toggled, and this 1 will remain as it is. So after third negative edge of the clock, the output will be 1 0 1. The state number is 4 and its decimal equivalent is 5. Now we will see the operation at fourth negative edge of the clock. Before that, I will write the outputs 1 0 1. Their complemented output will be 0 1 0. Now as soon as the first negative edge receives this flip-flop A, it will get toggled. This 1 will get changed to 0 now, and this 0 will get changed to 1. Now this 0 to 1 transition will give positive edge to this flip-flop B, so it will not get toggled. This 0 will remain as it is as it is, that is, it will be 0, and this QB complement will not also get changed, by which this flip-flop C receives the positive level as a clock input, so it will not get toggled, and this 1 will remain as it is. So after fourth negative edge of the clock, the outputs are 1 0 0. State number is 5 and decimal equivalent is 4. Now as we see, the counting starts from 7 6 5 4 in decreasing order. Therefore this counter is called as a down counter. Note that all the outputs are changing their state, but changes do not take place simultaneously, therefore this counter is called as a asynchronous counter. The same operation will goes on repeating, and counter outputs will change their values from 111 to 000. After reaching 001, the counter output will become 000, and the operation repeats itself for the next negative edges of the clock pulse. So this is the timing diagram of the 3-bit asynchronous down counter. These are the three outputs of the 3-bit asynchronous down counter. The outputs are changing at every negative edge of the clock input, and these are the 8 states of the counter output. This is the state diagram. This 0 is the initial state of the counter. After that, counting starts from 7 and end at 1. After this, the process goes on repeating at every negative edge of the clock pulses. This is the 4-bit asynchronous down counter, which consists of 4 flip-flops A, B, C, D. Each JK input is connected to the logic 1 input, by which its output get toggled at the negative edges of the clock pulse. Each flip-flop is negative edge triggered flip-flop, so the operation is same for this also. Only the difference is it is a 4-bit counter, by which it will count from 1111 to 0000. This is the truth table for the 4-bit asynchronous down counter. As I said, the counting starts from this 111, that is 15, and ends with 000, that is 0, at successive negative edges of the clock input. This is the timing diagram for 4-bit asynchronous down counter. These are the 4 outputs of the flip-flop, and they get changed at every negative edge of the clock input. And these are the 16 states of the counter. Till now we have studied the up counter and down counter separately, but in practice both these modes are generally combined together and an up down counter is formed. A mode control M input is also provided to select either up count or down count mode operation. A combinational circuit is required to design and use between each pair of the flip-flops in order to achieve up-down counters. There are two types of up-down counter, that is asynchronous up-down counter and synchronous up-down counter. Asynchronous counters are also called as a ripple counter. Now from these two, first we will see this asynchronous ripple counter. In up-down ripple counter, all the flip-flops operate in toggle mode. So either T flip-flop or JK flip-flops are to be used, as we have seen in up counter and down counter. The LSB flip-flop, that is first flip-flop, receives the external clock directly, but clock to every other flip-flop is obtained from Q or Q complemented output of previous flip-flop through the combinational circuit. As we know, in asynchronous counter, the Q output of previous flip-flop is connected as clock input to the next flip-flop, whereas in asynchronous down counter, complemented Q output of previous flip-flop is connected as clock input to the next flip-flop. We know for a ripple counter, as we discussed earlier, the Q output of previous flip-flop is connected to the clock input of next flip-flop, whereas in down counter, the complemented Q output of previous flip-flop is connected to the clock input of next flip-flop. So the selection of Q or Q complement output of the previous flip-flop be controlled by the mode control input M, such that if M is 0, the counter should count in up direction. So we have to connect a Q output of previous flip-flop as a clock input to the next flip-flop. If M is 1, the counter should be operated as a down counter. In that case, the Q complemented output of previous flip-flop should be connected as clock input to the next flip-flop. Now we will see how this is possible. This is the diagram for 3-bit asynchronous up-down counter, which consists of 3 T flip-flops whose T inputs are connected permanently to the VCC, that is to the logic 1. This first flip-flop receives the external clock input, whereas this second flip-flop receives the clock input from the Q or Q complement output through this combinational circuit. Similarly, this flip-flop receives the clock input from the QB or QB complemented output through this combinational circuit. A mode control input is also connected to the AND gates of this combinational circuit 1, 2, 3 and 4. Now with M as a 0, this circuit behaves as a up counting. Now we will see how this can be possible. Now as M is 0, this line is of 0 and M complement will be 1. This line is of 1. So M is 0, the AND gate 2 receives 1 input as a 0, AND gate 4 will receive 1 input as a 0. So irrespective of other input at this point, irrespective of other inputs to the AND gate 2 and 4, their output will always be 0. Means AND gate 2 and 4 will be disabled as M is 0, whereas this M complement is 1, so this AND gate 1 will receive 1, AND gate 3 will receive 1. So depending on the other input to the AND gate 1, the AND gate 3, their output will going to be decided. Means this AND gate 1 will give the value of QA as output, and this AND gate 3 will give the value of QB as output. So ORing these two, we will get the QA output as a clock input to this flip-flop and this QB output as a clock input to this flip-flop. So if you observe, the normal output, that is Q output of previous flip-flop, is connecting as a clock input to the next flip-flop, which is the same as that of normal up counter. So we can, from this we can say that this counter is going to be operated as a up counter as the mode select input is 0. So with M0, the AND gate 1 and 3 will be enabled, the AND gate 2 and 4 will be disabled, by which normal output of previous flip-flop will be connecting as a clock input to the next flip-flop. Therefore this counter acts as a up counter. Now we will see with mode control input as a 1, the circuit is same, only the value of M is changed from 0 to 1. Now this line will be of 1 and this M complement line will be of 0. So as M is 1, this AND gate 2 will receive now 1, this AND gate 4 will receive now 1, and as M complement is 0, AND gate 1 will receive 0, AND gate 3 will receive 0 as one of its input. Irrespective of other input, AND gate 1 will output 0, irrespective of another input, AND gate 3 will output 0. Now AND gate 2 has one input as a 1 and other input as a QA complement, so it will outputs the value of QA complement at its output, and AND gate 4 will have other input as a QB complement, so 1 into QB complement will gives you the value of QB complement at the output of AND gate 4. So by this ORing will connect the QA complement value as a clock input to this flip-flop. This ORing will connect the QB complement as a clock input to this flip-flop. So if we observe, the complemented output of previous flip-flop is connecting as a clock input to the next flip-flop through this combinational circuit. This is same as that of the normal down counter. Therefore we can say with m is equal to 1, the counter acts as a down counter. So with m is equal to 1, the AND gates 2 and 4 are active now, whereas AND gate 1 and 3 are disabled. These are the timing diagrams of up counting, and this is the timing diagram of down counting. In up counting, counting starts in ascending order, whereas in down counting, counting starts in descending order. Here it should be 1 1 1, that is 7, 1 1 0, 1 0 1, 1 0 0, 0 1 1, 0 1 0, and 0 0 1, like this. It is wrong. The value I have written in red color, those are correct values for down counting. Means it starts from 7 and ends with 0, whereas in up counting, counting starts from 1 and ends with 7, and after that the same cycle goes on repeating for the rest of the negative edges of the clock pulses. Now this is the 4-bit up down ripple counter, which is same as that of 3-bit. The only difference is that it consists of one extra flip-flop, so it will count 16 clock pulses from 0 to 15 in up direction, or it will count the 16 clock pulses from 15 to 0 in case of down counting. Now we will see the disadvantages of ripple counter. Every flip-flop has its own propagation delay. In ripple counter, the output of previous flip-flop is connected as clock for the next flip-flop. Hence propagation delay goes on accumulating. This accumulated time delay is the main problem with the ripple counter, because the propagation delay goes on increasing with increase in number of flip-flops. So this is the disadvantage of ripple counter. We will see the next part of this, means how to overcome the disadvantage of the ripple counter, in the next lecture. So in today's lecture we studied asynchronous down counter, 3-bit asynchronous down counter, and 4-bit asynchronous down counter. After that we have studied the up down counter, in which we studied 3-bit up down ripple counter. Thank you.